Okay. So is it warming up? Okay. So good afternoon, guys. Today we don't have much material to cover. I just will talk about the training of large language models and tricks, and also about different positional encodings, how to capture like long sequence in as input in our large language models. And if you have any questions about homeworks, also I'll take these questions. So the first question to you, do you need an extension for homework with attention?
I mean, I wouldn't complain with an extension.
Yeah, because it's maybe the most important topic that I want you to understand. So we can uh, extend this for 1 week, because the next homework on BERT is just running this training loop on the output from the BERT for the data set with paired questions. So it's maybe 1 hour work. Okay, so do you have any questions about this homework? Like in the beginning of class, I had a question about different models. Like, could you remind your name, please?
Jacob.
Jacob. Jacob tried to implement multi-head attention instead of simple attention. I even didn't think about this modification, because I was thinking that instead of applying attention to the input to our recurrent cell, you can apply attention, for example, to the concatenation of input hidden and input token. So this also valid. And actually, I believe this was used in one of the papers. But then people noticed that if you apply attention only to the hidden, it performs the same. Then instead of using attention concatenation in the input, you can use concatenation in the output before logits, before linear layer. So I think these are most simple modifications. Okay, so as you remember, yeah, transformer consists of 3 parts. Self-attention in encoder, self-attention in decoder, and attention between encoder and decoder. And also positional embeddings. BERT model is just the encoder of this architecture, and it was trained on the outputs from CLF's token and 15% of tokens which were applied masking or substitution or used unchanged. So only through these tokens, the gradients were flowing during training. But because we applied this on different batches, so gradients flew through all, in the end of the day, they flew through all the tokens. Um, okay. So let's talk about the size of the models. So for the first model, so next week we'll talk about GPT model, but let's just look at the sizes. For the first model, GPT-1, the size was 100 million weights, and it was trained on 5 gigabyte of data. For next model, the size of model increased about 10 times, and it was trained on more than 10 times, no, also about 10 times more data. So the difference between GPT-1 and GPT-2 is just that they used more data in OpenAI, but the performance increased. For and for GPT-3, yes, the size increased again by 100, yeah, by 100 times more. And also the number of data also increased by 100. So that's why now we have, we call this large language models, because the size of these models is large. But if you think about word embeddings, as you remember, it we had to wait while these weights were uploading for our word embeddings. So the size of word embeddings can be also very large and actually greater than large language models, because for each word we create the embedding and the number of words is large. But those word embeddings we don't call large language models, even though the size of word embeddings is large. Okay, so let's talk about tricks for training these large models, because the main problem with deep learning is to force our model to converge. And that's why we don't train these large models from scratch. We use pre-trained, and pre-trained models, they actually converge to something and to some minimum. So it's easier just to update the weights. But if you try to train this transformer from scratch, then there are two problems. One problem is the resources. You may need to use parallel computations and compute the gradients for one batch incrementally, even for one batch. And the other problem is that just to force your model to converge. And one of the tricks that was used to train these large models was to apply so-called warm-up schedule for learning rate. As maybe you know, in Torch there is function scheduler. Scheduler will change the learning rate with increasing of the number of steps of your training. And typically we decrease our learning rate. Like after, for example, 10 steps, decrease by 10 after or whatever. So there are different parameters. It was noticed that for large language models, it's a good practice to increase, not decrease, but increase learning rate. And only after some periods of increasing, start to decrease this learning rate. And here is the plot that illustrates the number of steps for this increasing learning rate. So if you increase the learning rate very fast, like for the first red point, then the model won't converge. So this increasing period also, the slope shouldn't be very high. So the second observation is about batch size. You can see that for small batch sizes, the performance, the loss of our function, and in this case, they used blue metric, so loss is high, but the blue metric is low because blue is better when it's higher. So for small batch size, it doesn't converge well. It doesn't converge to the good minimum of our loss function. So that's why the other problem with training large language models is to process a large batch size during one iteration. And again, it won't fit typically in the memory, and then you will need to apply incremental update of these weights. So you can calculate gradients for the part of batch size, then gradients to the second part of the batch size, and finally sum averages them, and only after that apply optimizer step. Oh, sorry, optimizer step, yes. Backward will calculate gradients. So this is the second observation. Then it was noticed that Adam optimizer works well for training, even though there are hundreds or maybe more different optimizers people proposed for training large language models, but as practice shows, just Adam works well. So the decay after warm up, it was noticed that it works well if it just is a square root of the time steps. And what else? Yeah, it's also there are many tricks to pre-process the texts, like to clean them, and it also helps the convergence. The other trick to use so-called mixed precision, and in your homework on the BERT, there's also one suggestion to use mixed precision. So you don't need to to use calculations, for example, in float 32 or 64, you can use float 16 calculations. Okay, so let's talk about the positional encodings. As you remember, in the standard, like original BERT model, the input size was 512 tokens. In the next models of BERT, the input size they increased, and it was 2048 tokens, so it's about 2 pages of text. But as you can imagine, when we apply attention to this input text, then if the inputs text will be longer, then we will need to use longer layers in our attention, so it will increase the model size. So that's why there is the problem with hardware to increase the input size to these models. But nowadays, like ChatGPT, it looks at the previous history, and we will talk about how we can actually process longer context. So, as you remember, in the original model, transformer model, in the paper Attention is All You Need, they used the fixed positional encodings with sines and cosines of some numbers. So in BERT, they used in BERT they used pre-trained positional encodings. So they just trained this positional encodings during training a large language model, and then used that pre-trained vectors, just adding them to the input tokens in the first version of BERT. So the next idea was to use just small context. Instead of adding positional encodings to every token, so this is the idea of relative position encoding. Let's create the positional encodings only for example, 5 tokens to the left and 5 tokens to the right. And to the tokens with index greater relative, because so token that is farther away from our current token by 5 position, we will use the same, the same number for a token on distance 10. For the token on distance 100, we will use just the same vector as position encoding. And it's clear intuition behind this, that the smaller context is more relevant. But if we keep less encodings, then we use less memory as well. So we can train this matrix of relevant positional encodings as relevant, and then it was added to our input tokens, and this is how the model was trained with smaller number of parameters. The next modification of the positional encodings, So the previous one is called relative position encoding. The second modification is called rotary position, rotary embeddings, and those are used in many versions of llama models, rotary embeddings. So the idea for this rotary embeddings was to use this rotation matrix. So the matrix 2 by 2 with sines and cosines, if you multiply this matrix by a vector, it will rotate this vector by the angle, in this case m theta 1. So that's why it's called rotary embeddings. It will kind of rotate every component of your embedding by different angle. And you can see that the last component will have the smallest angle. So it will make the full period faster for the first components, and it will make the full period only after many steps, well, not steps, but the idea is that the angle will be smaller for larger indices. And the idea behind this was that if we have two words, two tokens with similar embeddings, the rotary embeddings will somehow change the direction of these tokens. And because they are used inside transformer, like inside this relative attention, so the model also will add some weights to this rotary embeddings, and they will learn how to rotate the embeddings for words with similar positions and for words with like longer larger distance, and if the words have like larger distance between, the distance is larger between the words, then this matrix will rotate these words like by larger angle, and will make these words less similar. So again, the same idea that for the words on large distance, we will consider them like less important. So this is the idea of rotary embeddings. And here's the comparison of more training stability with relative position embeddings, rotary embeddings, and learned embeddings, which were used in BERT. So you can see that rotary embeddings actually are more stable for training. That's why they are used in modern versions of large language models. They're more stable than rotary than relative position embeddings. The other way to add in this to encode position is called alibi embeddings, which stands for add a linear bias. So this is the very simple idea. Just add a larger number for embedding with larger position. So just a simple addition of constants. That's why it's called add a linear bias. And this factor m also will decrease as power of 2. So for rods on the larger distance, this additional term will be smaller because of this m, because m will decrease with the index of the position. So, and it also performs well, and some versions of Llama are trained with alibi embeddings, some versions are trained with rotary embeddings. So it's interesting that, okay, it's plot a little bit cut. So for trainable embeddings, if we try to apply trainable embeddings to the input size longer than it was trained on, then the accuracy of the model will decrease. But if we use this alibi at linear bias embeddings, then even for very long input sequences, it will perform well. So that's why they're used in the modern language models. So somehow they are stable for longer input sequences, even though they were not trained on this size of inputs. Yeah, so this is just information about which positional embeddings are used in which model. Well, there is another trick in feed-forward module. As you remember, after attention, there is also feed-forward module with 2 linear layers. People also noticed that if we add some nonlinearity for this feed-forward linear layer, then it will perform like a gating mechanism, like sigmoid is, for example, between 0 and 1. It means that it will kind of drop some neurons in this feed-forward layer, and they call this gated linear unit. So it also increases the performance, and you can use different activation functions, and there is comparison which activation functions actually perform better. But The difference is just not really significant. It's just in some decimals or maximum in just units. Okay, now let's talk about modifications of this vanilla BERT model. So do you know how this BERT model looks like? If you don't know, it's the left from this yellow bird. So now you can consider yourself as specialists on large language models. You know how BERT model looks like. So people, of course, try to modify this original BERT model and tried different things. So one thing was, why should we train the model on the pairs of sentences? Why actually do we need this next sentence prediction task? And it turned out that we don't need that. Because for the first model, people just tried something and it worked. But then people tried other things. And so the first observation was that it's unnecessary to use the next sentence prediction task. The masking is enough. So the other modification that they did in this Roberta, so raw because they used rotary embeddings. They also applied so-called dynamic masking. In original BERT model, they applied mask and didn't change this mask tokens over training. In Roberta, they masked these tokens differently for every batch. And it also improves the performance. So these are some metrics. So if you want to publish a paper, then you should compare your model with the BERT model. So every paper in NLP compares their results with BERT, but the BERT is the first model, and of course it has the worst performance on all the tasks. Even though, of course, it performs well on the task better than previous methods, but still, every time you will see the comparison with BERT model, because of course it has lower scores on all the tasks. So what's next? The other modification of BERT model is called Electra. It's not used now, I think, anymore. Almost not used. So the idea was to train two models. The first model generator is the BERT, the transformer, encoder of transformer. And the second model is also transformer, but it wasn't it was trained separately. So so this architecture is a little bit similar to Gantt's model when we have generator and discriminator, but in Gantt's model we use discriminator to improve generator. In this case, we don't use discriminator when we train generator at all. But it was noticed that if we kind of stack two models, then the embeddings, the output embeddings from the second model, from discriminator, will perform better on NLP tasks. So yeah. Again, some metrics. Oh no, these are just parameters. Okay, so the other modification of BERT was to use encoder and decoder, because in transformer we have encoder and decoder, and this model was called BART model. So in BART model, oh, by the way, because we don't have any more next sentence prediction task, instead of classifier token, CLS, they use this starts token, S. So, for example, yes, when you will use Roberto or DBERT, you don't have this CLS token anymore, but still you will use typically the starter token for classification as the embedding of the entire input sentence. So I don't want to, because we didn't cover GPT, I don't want to talk now about BART. So yeah, let's look at DBERT. So I recommend to use DBERT for your next homework for similar questions search. So DBERT has architecture similar to Electra. And there is a popular model T5, which is a combination of encoder and decoder. Let's see if we have next slide. Yep. So and there is also model T0. So people try to train the same model on different NLP tasks sequentially. So first they train, for example, on the text summarization. After fine-tuning on text summarization, they train the same model, fine-tuned model, on sentiment analysis. Then they used this model fine-tuned on two previous tasks on the third one. And after that, it turned out that the model that was fine-tuned on these different tasks sequentially actually can perform all these tasks. So it's kind of united. So one model that can be applied to different tasks, and it performs well on different tasks. But this is encoder decoder model, kind of BART. And also people try to use as input to the model other modalities, for example, images. And if you use, for example, image transformer, visual transformer, it works kind of word to vec. Word to vec created embeddings for words. Image transformer can create embeddings for images. And there is also WAV to VEC, the model that creates embeddings for audio data. So you can use these embeddings as input to your large language model in attention layer. And your attention will look not only at the text, but also at the embeddings of input images, for example. And if you will fine-tune this model on some tasks like image recognition, then this model, it's called Flamingo, you can type the text and image, and for example, what is in this image, and it will provide the text that there is a cat on this image and something like that. Yeah, so this is example of the prompts. Like image, and then this is, and then the model continues. This is a flamingo. Okay, now let's talk about interpretability of the model. Oh, wait a second. We have just 3 minutes left. Okay, but I want to finish our previous topic. Let's see. Hmm. Um, yeah, so I don't want to leave this for next week. So when people, so first of all, we talked about attention in large language models and transformers. These fully connected layers, actually, I kind of mentioned that they learn the probabilities of the next tokens. So then people try to evaluate this on the classical NLP tasks, and like P was part of speech classification, name density recognition, and so on. And in classical NLP, before neural networks, they considered like part of speech the simple problem. So they solved this problem and they applied the results to the next problem to find the constituents. I don't remember. It's noun phrase. Like something is compared with adjective. So, and they applied every task to solve the next task that they considered harder. So when they looked at the output from BERT model, you can see that like shallow layers, they learn actually these tasks that linguists considered easier. And more deeper layers, they learn more complex tasks. So at this point, these linguists that didn't like neural networks were happy because they said, oh, we were right that we use this sequence of the tasks because even BERT understands that these tasks are more difficult or easier looking at the depth of these layers. Okay, so let's stop here. And next week we will start GPT model. So yeah, and we will extend the homeworks by 1 week again.
Hmm.